Alright, so our next video is CC2, separating mixtures. Again, you would have done this way back in year 9. I'm starting off, we're just going to clarify what we mean by something that's pure and something that's a mixture. So if something is pure, you should only have one type of substance. So if I had a beaker that contained, let's say, pure oxygen, I should have O2 in there and absolutely nothing else. If I had a beaker that was pure water, water is H2O, so I should have H2O in my beaker of water and I shouldn't have anything else. If it's a mixture though, I'm going to have a few different things. So your classic example is the air around us is a mixture. So we've done the atmosphere recently and we learned that it contained nitrogen and it contained oxygen and it contained carbon dioxide and also a small amount of argon. Okay, so I've got 4 different things all mixed together. That's a mixture. Whereas something that's pure, there's only one type of thing, be it O2, be it H2O, be it CO2, but there's just one type of thing if it is pure. And you can tell a pure substance from a mixture using melting point, all right? So I'm going to draw a little graph here to the side, similar to what we drew in CC1, okay? I'm going to draw one of these kind of heating curves, okay, and we know that the flat bit, that this here represents a state change, and if your substance is pure, okay, which this one is, your state change occurs at the same temperature, so you get that nice flat bit. So let's just say this is pure water, it will melt at 0 degrees Celsius. If you had something that was impure, it would end up looking a little bit something like this. You're heating it, and then the state starts to change, but you don't get a dead straight line at the state change because it doesn't all melt at the same point. It's not all melting at the same point because it's made of different substances. So the way we phrase this is we say pure substances have a sharp melting point, and that literally just means if it's pure, it all melts at exactly the same temperature. An impure substance has a melting point range, and that means because it's impure, it might start to melt at 10 degrees Celsius, but it might not finish melting until 15 degrees Celsius because it's impure and there's more than one melting point involved. Alright, press pause, have a go at questions 1 and 2. Alright, if we look at the first question, you're asked to identify which is pure, which is a mixture. Okay, A is pure. There's only grey circles, it's all the same thing. C is pure. Only white circles, they're all the same thing. E is pure, black circles, they're all the same thing. If we have a look at D, you've got a black circle surrounded by 3 white circles. So this is one thing, but everything is the same. It's always one black circle surrounded by 3 white circles. That is pure. B, on the other hand, you've got a black and a grey circle, and you've got that again, and you've got that again, but you've got it mixed in with these white circles. So B, that one is going to be impure, or you're a mixture. In terms of your melting points, okay, if it's pure, it's got a sharp melting point, so it might melt at 50 degrees Celsius, just one temperature. If it's impure, it's got a melting point range. Maybe it starts melting at 50, but it doesn't finish melting until 55 because you've got more than one thing in there. Alright, the rest of this topic looks at how we are going to separate mixtures. Okay, first mixture we're going to look at is a mixture of a liquid and an insoluble solid. If it's insoluble, it does not dissolve. So your example here, I'm going to write e.g. might be sand and water. So sand will not dissolve in water. So you need to be able to draw out the apparatus. Okay, so we're going to do that now. So this is the flask that I would use. Okay, if I label this, it is a conical flask. Into the conical flask, I'm going to put a funnel. Alright, so label that as funnel. And then into the funnel, you need to put filter paper. Okay, so all of these things need to be labeled filter paper. So this is the apparatus, the equipment that I would use. So funnel's on the outside, filter paper is inside it, and then you've got your conical flask. And what you would do is you would pour your sand and your water here into the filter paper. All of the water would be able to pass through the little holes and come down here. So my water will end up in the conical flask, but my sand is going to get stuck in the filter paper, and it's going to stay in the filter paper. We call whatever gets stuck in the filter paper, we call that the residue, and whatever passes through the filter paper, we call that the filtrate. The technique is called filtration. Okay, so that's what the technique is called, filtration. That's how we separate an insoluble solid, something that doesn't dissolve, from a liquid. Next one we're going to look at is how we would separate a liquid from a soluble solid. An example, soluble just means it does dissolve, and your classic example here would be salt and water. Salt and water. Okay, so if I try to use my filter, because the salt is dissolved in the water, it will just pass straight through the filter paper. Nothing will be trapped in the filter paper. Everything will just end up in the conical flask, which is no good to me. So instead, I'm going to use a different technique, crystallization. And I'm going to draw the apparatus I would need. Okay, I'm going to draw myself a little basin, and then I'm going to draw a tripod. I'm going to draw a Bunsen burner. Okay, so this is called an evaporating basin, evaporating dish. This is my Bunsen burner. Okay, and what we would do is we would put the salt and the water would go in here. So the salt and water would go in here, and then when you heat, because the water evaporates, okay, and the salt is left behind, we're able to separate the salt from the water. So to describe this in words, you would just write heat. You would say the water evaporates, and you would say salt crystals are left behind. Okay, so you heat, you evaporate the water, and then the salt crystals are left behind. You do have to heat slowly, okay? You don't blast it with heat or it can turn into mush. To get nice big crystals, you want to heat it slowly, evaporate off some of the water, and then you'll be left with some nice salt crystals. So this method would be called filtration. This method down here is called crystallization. All right, have a go at doing questions. Where are they? 3 and 4 for me, please. Have a go at 3 and 4. So press pause, do 3 and 4. Right, here's your apparatus. Remember, apparatus just means equipment. Sand is insoluble, so I would use filtration. You need to have conical flask, funnel, and then inside the funnel you've got the filter paper. Salt is soluble in water, so I would use an evaporating dish on some source of heat. So you can write the word heat, or you can draw a Bunsen burner. Alright, we're now going to look at another technique to separate salt and water. Imagine you were stuck in an island and you needed to drink seawater, but you need to remove the salt first. If we look at the method back here, crystallization, we separated them, okay, but our water just evaporates and you're left with salt in a dish, but the water is totally gone. What if you wanted to actually keep the water as well as keep the salt? You would need something slightly more sophisticated. So that's what we're going to do now, okay, and it's called distillation. And it looks like this, alright? So you start off with a round bottomed flask. That's literally what it's called, a round bottomed flask, okay? And in the round bottomed flask, you are going to put your salt and you are going to put your water. Your salt water is going to go in there, okay? And you're going to heat your round bottomed flask, okay? So I'm going to use a Bunsen burner to heat it, okay? And when I do, I know the water is going to evaporate. But rather than letting all of that water escape, I'm going to capture the water vapor, and I'm going to turn it back into liquid water. So to do that, I'm going to have something coming up here, and then coming down here like this. All right. And when I heat now, the water vapor is going to rise, and I'm going to block the top here with a little lid and a thermometer. Okay, so it's going to rise, and then the water is going to be forced to enter this tube. Now I'm just going to draw a picture of that. Right, so there's water, your water. Okay, so in this tube here, you have got water vapor. So H2O as a gas is going to rise up here. And then the gas is going to be directed into this tube, but I don't want it as steam, I want it as liquid water. So how am I going to go from water as a gas back to water as a liquid? Well, I need to condense it, and for that I'm going to need to cool it down. So I need this tube to be really, really cold. And to make this tube really, really cold, I attach what's called a condenser around it. So around that I have put a condenser, and I attach my condenser to the sink, okay, and I've got cold water coming in at the bottom, and the cold water from the tap goes out at the top. And because it's fresh water from the tap that you're running around this tube, the tube stays really, really cold. And then all you need to do at the end is put a little beaker. Okay, so your water vapor will rise up here, it will come into this tube, it will get nice and cold, okay, so it will turn back into a liquid, and then here at the end you're going to collect your liquid. Okay, the salt isn't going to change state at all. The salt will just stay in your round bottom flask. So it's just the water that turns into a gas, then you cool it down in the condenser and it becomes a liquid again. Just a few things to notice. I'll put this on your carousel, okay? But the water goes in at the bottom, they've asked that before, and comes out at the top from the condenser. There was one question where they had the labels the other way around and they asked you what mistake had been made. So in at the bottom, out at the top. The other thing is where the thermometer goes. So you need to have a thermometer just to check the temperature, and the thermometer, the bulb of the thermometer has to be in line with the entrance to the condenser. Again, they had an exam question where they put the thermometer right down into the round bottomed flask, and that was incorrect. Your thermometer should be up here. And the other thing they did wrong was this beaker here that I'm using to collect the water, they just moved it over here. You have to obviously have it directly underneath the condenser so that you can catch all of the water coming out. All right, so go back to your questions. A much nicer picture of distillation here. Can you have a go at doing question 5 for me, please? Alright, so in the round bottom flask you are heating the water, and then the water will evaporate. You can also write boiling. Then that water vapor comes up here, comes down here, and it's cooled down, and when you cool it down you get condensation. The question that this came from, it asked you to label A. A is called the condenser, so that's what the label A would be for. Right, they have also asked before how you separate a mixture of gases. So in the atmosphere we've got nitrogen, oxygen, carbon dioxide. How would you separate them? There's no technique that allows us to separate gases from each other. So what we would need to do is turn this mixture of gases into a mixture of liquids. Okay, so if they're all present as a liquid, okay, if I've got nitrogen, oxygen and CO2 all as liquids mixed together, then I'm going to be able to separate them. So if I want to go from gases to liquids, what do I have to do? Okay, I need to cool. I need to cool and condense. So if I cool and condense, I go from my mixture of gases to my mixture of liquids. And once I've got a mixture of liquids, we've seen this year, you can separate a mixture of liquids using fractional distillation. We looked at it when we looked at crude oil. Crude oil, distillation, crude oil is a mixture of liquids. Now I've got another mixture of liquids. I separate using fractional distillation. And the reason I'm able to separate them using this technique is they all have got different boiling points. They've got different boiling points, so I can use fractional distillation to separate them. All right, so just be aware of that one. I have seen it being asked before. The other thing that they ask more commonly is they'll ask you questions about chromatography. All right, so hopefully you remember this. chromatography, you've got your piece of paper, and on your piece of paper you draw a start line, and you draw that start line in pencil. Okay, so there's my start line, and I'm drawing it in pencil. And the reason I draw in pencil is if I drew it in ink, the ink would smudge. Okay, and on my start line I'm going to be putting the samples I'm trying to analyse. So I'm going to analyse sample A, and there's sample B, and I put a little dot on my start line. And then I take my chromatography paper and I put it into my solvent. Okay, so I'm going to put it into a beaker. There's my start line. And it's really important that when you first put it into the beaker that the water is below your start line. Alright, so this is your solvent, and it is typically water, and I want that to be below my start line. And then what's going to happen is that water is going to move the whole way up the page. Okay, and when it moves the whole way up the page, it's going to cause, sorry, there's my dots again. Alright, when it moves the whole way up the page, it's going to cause the different mixtures in the ink to separate, and at the very end this is what you end up with. Alright, so let's just say this first spot here, A, contains 3 different substances. It will separate out into 3 different dots, and let's just say here that the second spot, alright, that part of it stays on the start line, and then it separates out into another spot. Okay, so maybe they're my results. So start off my chromatography paper, draw my start line in pencil, put a little dot of my sample. Then I take my chromatography paper and I put it into the solvent, making sure that the solvent, which is usually water, is originally below my start line. The solvent is going to move up the paper, and when it does, it carries the different substances different distances. This spot here was made of 3 different things, and it separates them out into 3 different spots. This one here is made of 2 different things. It's separated out into 2 different spots, and these are my results that I then need to be able to answer questions on. So a few things on chromatography that they love to ask. Okay, number 1, they'll ask you what the stationary phase is. Okay, so the stationary phase is the paper itself. Okay, just a recall question, I'll put it on carousel. Stationary phase is the paper. They'll also ask you what the mobile phase is. The mobile phase is the solvent. In this case it's water, but it could be a different solvent. So they love to ask those questions. They also love to ask you questions about the results. Okay, so they'll say, how many different substances does substance A contain? We'll call this one A, and you'll say 3 because there are 3 dots. It might ask you a question about why this spot here didn't leave the start line. If it doesn't leave the start line, it's because that particular substance is insoluble in the solvent that you've chosen. So if it doesn't dissolve in water, it won't move. Now there obviously was another substance in here that was soluble in water and did move, but something wasn't soluble and something stayed on the start line. So that's what happens when you get something left behind. If you had a pure substance, okay, you would get 1 dot and 1 dot only. We'll do lots of exam questions on chromatography because they do tend to ask it, but I want you to have a look at questions on the next page. All right, I want you to do 6, 7 and 8. Okay, do 6, 7 and 8. See how you get on with those questions, and then I'll go through them. All right, 6, stationary phase is the paper, mobile phase is the solvent. All right, over here, this is the results. What's used to draw the start line? Pencil. Okay, why? Because the pen would smudge. How many substances does black ink contain? Here's your black ink. You've got 1, 2, 3 dots, and therefore it contains 3 substances. What colors? All right, so if you have a look, all right, the black ink contains the same spot as this one, and this is red. The black ink also contains this spot, which is over here, and it's blue. And then the black contains this one, all right, which isn't anywhere. It doesn't map onto any color. So I will say red, blue, and an unknown color. We don't know what it is. okay? It doesn't contain any green, because if it did, it would have a spot exactly the same height as the green one. The other thing that they ask you to do with chromatography is they ask you to calculate RF value, and they usually give you the formula for it, but it's the distance the spot moves divided by the difference the solvent moves. So let's just say they told you that that green spot had moved 5 centimeters, okay? You're going to put 5 centimeters divided by, and let's just say they tell you that this distance here is 10 centimeters. You're going to have 5 over 10, and you're going to get 0.5. So it's the distance moved by the spot divided by the distance moved by the solvent, and you can see they've marked the solvent there with a line. Your RF value should always be less than 1, always. So if you're confused about which way around to put the numbers, if you get an answer that's bigger than 1, you've done it wrong, okay? It's always small number on top, big number on the bottom. Right, last little thing here is about potable water, which I'm not really going to draw diagrams for because I can't. Hopefully you remember some of this. Potable water is just water that's drinkable, okay? It doesn't need to be pure. The water we get out of our taps, the water we get in bottled water, it's not pure. There are minerals in that water that are good for us. Things like calcium, okay, are in that water that are good for us. So it's not pure, but it is safe to drink. So it's drinkable or safe to drink. How do we make potable water? Okay, it's because we use water from like the rivers, okay? Obviously drinking from the river would not be safe, so we need to do something to it. So we go through 3 processes. One is filtration. We filter out all the twigs and the, I don't know, plastic bags that you might have floating around in the river. Then you go through a process called sedimentation. And in sedimentation, you basically just let the water sit in a big tank and let all of the little bits floating around in the water sink to the bottom. So all the bits just fall to the bottom. And then at the very end, you're going to add some chlorine. And my next question is, why do we add chlorine? Chlorine kills bacteria, all right? Without adding chlorine, there'd be all sorts of little microorganisms in there, which would make us incredibly sick. Now, we purify groundwater. By groundwater, I mean water that we get in rivers or in lakes. We do not purify seawater. The reason, if you needed to purify seawater, you would need to remove salt. And what we've seen earlier on today is if you want to remove salt from water, but keep the water, you need to do distillation. Now, distillation works really well, all right, but if we go back and remind ourselves what distillation looks like, okay, you would need to heat huge volumes of water to be able to purify enough for everyone to drink. And if you're heating huge volumes of water, that is very expensive. So doing distillation on a large scale is too expensive, okay? It's way too expensive. So rather than trying to purify seawater and remove all the salt, we purify groundwater, okay, or fresh water, which, yeah, the Thames might have, you know, plastic bags and twigs and all sorts of stuff floating around in it, but it's easier to remove those things using filtration and sedimentation and chlorine than trying to remove all of the salt from seawater. So that is what we use. Right, again, we're going to do loads of exam questions on this topic in the lesson, but also make sure you are doing your carousel quiz.